Hello, everyone. I'm Theodoros ADAMANTOPOULOS. I'm a PhD student in Forschung Zentrum Jülich. And today I'll talk to you about angular momentum transport in optically excited antiferromagnets from ab initio. Before starting, I would like to thank the organizers for inviting me here today. And I would also like to thank my supervisors, Yuri Mokrusov, Stefan Blugel, and also my colleagues who also participated in this work. So in Spintronics, so far, we've been taking advantage of the spin momentum degree of freedom, and spin transport and spin dynamics have been studied so far extensively. Recently, people started looking into the orbital angular momentum degree of freedom, and from studies on orbital Hall effects and orbital dynamics, the new field of orbitronics has been introduced. Our work is focused on the exploration of laser-driven currents of angular momentums in antiferromagnets and other materials as well. Concerning spin photocurrents, they have been studied in various materials like graphene, semiconductors, quantum wells, organic systems. And they have been expected to have many applications, for example, contact-less generation of spin currents and their injection. They were expected to mediate the optically driven torques of the magnetization and also to provide means to read out the magnetization direction. For this reason, there is an ongoing quest for angular momentum current generators, and antiferromagnets is among of these candidates. Usually, these spin photocurrents are accompanied by some kind of charge photocurrents. One easy example of charge photocurrents is from the well-known photovoltaic effect, where light shining on a p-n junction creates a charge photocurrent which flows along the direction where the inversion symmetry is broken. One other type of current is what I will call as the magnetic currents. These appear from linearly polarized light in an effect which is called the linear photogalvanic effect in materials with broken inversion symmetry. These are magnetic currents because they are driven from the magnetization and they are odd in it, and they are also bound to spin currents. One easy way to access those photocurrents is through the well-known setup of the Spintronics Terahertz emitter. On this setup, we have a ferromagnetic layer which is in-plane magnetized, and it is coupled to a non-magnetic layer. When a femtosecond laser pulse acts on the ferromagnetic layer, a traditionally called super diffusive spin current is created without the need of spin-orbit coupling, and then it flows into and is injected into the substrate. Then it flows through the non-magnetic layer, and it is converged into an in-plane charge photocurrent due to the inverse spin Hall effect. From this charge current, a broadband terahertz pulse is emitted, which is the trademark of the Spintronics Terahertz emitter. The currents that I discussed here are the linear photogalvanic effects current. We have an in-plane charge current which flows perpendicular to the magnetization. It is a magnetic current in the sense that it is odd in the magnetization. And it is also bound to a so-called diffusive spin current, which flows out of the plane throughout the slab with spin polarization parallel to the magnetization. In the next slides, I will discuss about the photocurrents in antiferromagnets and also about orbital photocurrents. Before moving there, I will first try to demonstrate to you with some simple symmetry arguments what kind of photocurrents we expect in a simple PT antiferromagnet. Starting from a non-relativistic scenario, we consider a slab where you have an in-plane magnetization along the y direction and a breaking of the inversion symmetry along the out-of-plane direction. Because of this breaking of the symmetry, we may expect one charge current which flows out of the plane. This is not a magnetic current because it occurs from the breaking of the inversion symmetry, and it is even in the time reversal symmetry. Applying the PT symmetry operation, this setup flips the magnetization and also flips the sign of this charge current so that it will overall vanish. This charge current may also carry some spin polarization, so we may expect a spin current which flows out of the plane with spin polarization parallel to the magnetization. Applying the PT symmetry operation reverses both the direction of the flow and of the spin polarization so that it will overall survive. This is the diffusive type of spin current that we've also seen before in the terahertz emitter, and it flows through the slab, it is odd in the magnetization, and it's polarized along it. When we take spin-orbit coupling into account from the breaking of the mirror symmetries, we may also have a charged photocurrent which flows out in the plane perpendicular to the magnetization. This is due to the magnetic photogalvanic effect, and this is a magnetic current which is odd in the time reversal symmetry. Applying the PT symmetry operation leaves this current unchanged. Additionally, we may also have a spin current which flows parallel to the magnetization with out of the plane spin polarization. This is due to the magnetic spin photogalvanic effect. And again, the PT symmetry operation here flips both the direction of the flow and of the spin polarization so that it will overall survive. And this type of spin current, I will name it as the spin Hall type of current. Again, it is odd in the magnetization, but it lives perpendicular to the charge current. The same arguments that I used here for the spin can also be used for the orbital angular momentum degree freedom. So far, in antiferromagnets, there have been studies of spin photocurrents, mainly in response to linearly polarized light. We have some reports of small in magnitude diffusive spin photocurrents. And also, when spin-orbit coupling was considered, there have been some larger in magnitude results in insulating antiferromagnets. This makes us expect that compensated metallic antiferromagnets might be very promising for the appearance of spin photocurrents. We explore manganese to gold, a famous electrically switchable, easily switchable, fully compensated PT antiferromagnet. In this material, the Nel vector is in plane along the 110 direction, and the magnetic moments cause a breaking of the inversion symmetry along the out of the plane direction. Throughout our calculations, we use the Keldy's formalism, which is a Green's function theory, in order to calculate the responses which are of second order in the electric field of the laser. And we use a typical value of 10 gigawatt per square meter for the laser intensity. And we are also able to vary parameters such as the lifetime broadening of the electronic states, the laser frequency, the Fermi level, and also the polarization of the light. We have a look at the spin photocurrents. On the left, you can see the spin Hall type, which flows parallel to the Nel vector. On the right, the diffusive type, which flows out of the plane. As you can see, they are both sizable, with the spin Hall type being almost one order of magnitude larger. And also, they behave differently in relation to the lifetime broadening. This lies to their different mechanism behind them. The spin Hall type originates from a Berry curvature dipole mechanism, whereas the diffusive type originates from a quantum metric dipole mechanism. Overall, by varying the parameters in our calculations, we are able to control the strength and the sign of the radiated spin currents, and our results are comparable or larger than in previously studied materials. One natural way to think of the photocurrents in manganese to gold is through what we call the photospin Hall effect. This is an attempt to perceive the photocurrents which appear because of the linear photogalvanic effect in a spin Hall geometry. From the action of the lepals, we have a flow of charged photocurrent perpendicular to the magnetization, which can act as a way to read out the magnetization direction. And at the same time, we have a pure spin current injection, either parallel to the Néel vector or out of the plane. Here, you can see on the left the charge current component, and on the right, the spin current component, the spin Hall type, parallel to the Néel vector, in relation to the laser frequency. They are both sizable, and they vary quite differently. And for this reason, I introduce the photospin Hall angle as the ratio of the spin to the charge photocurrents. And I plot it here in relation to the Fermi level. You can see that for a large region close to the Fermi level, it remains quite stable. And this is an indication that through the photospin Hall effect, we are able to generate robust spin photocurrents, which can even be measured in the DC nonlinear regime. The next part, I will talk about orbital currents. And these, through the last years, they have been shown that from current-induced orbital currents, we are able to switch the magnetization efficiently by introducing orbital torques in the ferromagnetic layer. And the advantage of the orbital torques is that they show a long-range behavior inside the ferromagnetic layer, in opposition to the spin torques, which oscillate and vanish after a while. This has been shown theoretically. So from calculations on chromium and iron cobalt bilayers, it has been shown that due to orbital traps, which act as hotspots of orbital angular momentum in the K-space, the current-induced orbital torque is larger and it has a long-range behavior in opposition to the spin-induced moment. Additionally, experimentally, there is a recent report of 50 nanometer decay length for the orbital angular momentum in nickel, titanium, tungsten bilayers. And these both are indications that we may have novel spin orbital dynamics in regimes which can reach length scales from 1 to 100 nanometers. This long-range behavior has also been seen in the ultrafast regime. In the first day, we had in the talk from Tom Seifert, we saw about their experiment, where apart from considering spin currents which mediate the terahertz emission, they also considered orbital currents to mediate the terahertz emission from the inverse orbital Hall effect. Here they had a layer of nickel coupled to several tungsten layers, and they saw that inside the tungsten layers there is a strong orbital to charge conversion, which exhibits exotic long-range ballistic behavior. And by studying the dependence on the tungsten layers, they highlighted the importance of lowering the crystal symmetry because this conversion takes place at the far end of the tungsten slab. With this study, we start to understand that it's very important to also study the photocurrents of orbital angular momentum. We go back to manganese to gold. We calculate the orbital photocurrents there, both type, the orbital Hall type and the diffusive type, and they are not impressive if we compare them to the spin photocurrents on this material. This can be explained from the fact that in this material, the inversion symmetry is broken only by the magnetic moments. We want systems where we have structurally broken inversion symmetry. And for this, we consider bismuth-silver surface, which is a system where a non-magnetic system where the orbital Rasba effect breaks the inversion symmetry and creates orbital angular momentum, chiral orbital angular momentum texture, as you can see here for the p states of bismuth. In fact, by simply breaking the structural inversion symmetry, we are able to boost the orbital photocurrents. even from a non-relativistic scenario, where we calculate large responses, robust, for a wide energy region where the bismuth p states are located, and which also scale with the value of the orbital Rashba constant. When we consider spin-orbit coupling, the orbital photocurrents remain unchanged in magnitude, but their robustness increases with the value of the laser frequency. On the other hand, the spin photocurrents are robust, but they become suppressed when we increase the laser frequency. To understand this behavior better, we have a look into the reciprocal space. And here you can see that the orbital response preserves its sign, whereas the spin response consists of areas with opposite sign, which when integrated lead to this suppression. Overall, we see that the orbital response is governed by the orbital Rashba effect and the crystal splitting, whereas the spin response becomes suppressed by the spin-orbit coupling. After studying the PT antiferromagnets like manganese to gold, we saw that the orbital currents there are not impressive, and we want to study materials which have the advantage of vanishing magnetization, but that also have broken structural inversion symmetry. And for this reason, we consider altermagnets. For altermagnets, we already heard from the talk of Thomas Jungwirth. I will not say much, only that in this new class of materials, we have compensated magnetization and alternating spin splitting in K-space. Ruthenium dioxide is one famous prototype altermagnet. There has been a report of large spin splitting and very large crystal Hall effect in this material. And our goal is to employ this structural complexity of the altermagnets in order to go away from PT antiferromagnets. Unfortunately, ruthenium dioxide has inversion symmetry, so we don't like it. And we asked Libor Smejkal about an altermagnet which has broken inversion symmetry, and he proposed to us this vanadium niobium sulfur. This is a TMD-based intercalated altermagnet with structurally broken inversion symmetry and with in-plane magnetization. Here on in the band structure, you can see how large the spin splitting of the state is. We calculate the orbital photocurrents in this material, and they are surprisingly, they are very, very large. They are one order larger from the spin photocurrents in manganese to gold. And then they are also 2 orders of magnitude larger than the spin photocurrents on this same material. In fact, we see here again how important the breaking of the inversion symmetry is in order to boost the orbital photocurrents. In a last step, we become motivated from a recent consideration of current-induced generalized side-dependent spin or orbital currents, and we have a look into the atom-resolved laser-induced orbital photocurrents. We decompose them to non-staggered and staggered components, and as you can see, we were able to pick up a perfectly staggered component which flows parallel to the Néel vector with out-of-the-plane spin polarization. And this makes us think of a scenario where we have staggered orbital currents in an antiferromagnet that we might be able to use it as for side-dependent injection of angular momentum, and with possibly interesting dynamics following this injection. Closing, today I talked about metallic magnets that are accompanied by various types of photocurrents. I presented that metallic PT antiferromagnets can host various kinds of strong spin photocurrents. I introduced the photospin Hall effect as an efficient tool for spin injection. I talked about optically generated robust currents of orbital angular momentum. And I also introduced the altermagnets as a possible platform for orbital currents. And I discussed about sublattice dependent currents and responses, which may be very relevant in the future. Thank you.